In this video, we will discuss the relationship between force and motion as described by Newton's three laws. The first law. Newton's first law of force and motion tells us that if an object has a net force acting on it, it will accelerate in the direction of the net force. The acceleration, which is a change in velocity, can be a change in the velocity's magnitude, direction, or both. Because velocity is a vector, a change in direction is a change in velocity. And as a change in velocity is acceleration, a change in direction means the net force is acting on a body. The best location to study Newton's first law is in outer space, where the natural forces of gravity and the resistance offered by air molecules does not exist. In this slide, we have a spacecraft in outer space traveling at a constant velocity in a straight line. Because there are no net forces acting on the spacecraft, it'll travel at constant linear velocity forever. If we want to increase the magnitude of the velocity, we ignite the main burner at the rear of the spacecraft. The hot exhaust gases escaping the rear of the craft create a reaction force called thrust that accelerates the craft forward. If we want to change the direction of travel, we engage a side thruster that creates a net force, and the craft will change direction or accelerate in the direction of the net force. Newton's second law quantifies the first law and states that if a net force acts on a body, the body will accelerate in the direction of the net force, and the magnitude of the acceleration will be directly proportional to the net force exerted on the body and inversely proportional to the mass of the object. So the acceleration in meters per second squared equals the force in newtons divided by the mass of the object in kilograms. So if we double the net force and the mass of the object remains constant, we double the acceleration. If the net force remains constant and we double the mass of the object, the acceleration decreases by half. Because velocity and force are vectors and have direction, so does the acceleration. Example 1. A net force of 50 newtons acts on a 10 kilogram object in a direction due north. What is the acceleration? Acceleration equals force divided by mass. Acceleration equals 50 newtons divided by 10 kilograms. Acceleration equals 5 meters per second squared. So the object will accelerate at a rate of 5 meters per second squared in the same direction as the net force, due north. So, summing Newton's first and second laws, we can deduct from the first two laws that if a body is at rest or moving in a straight line at constant speed, then no net force is acting on the body. This doesn't mean there are no forces acting on the body. It means the effect of the force in one direction is negated by a force of equal magnitude in the opposite direction. Don't forget, forces are vectors. Newton's third law. Newton's third law deals with reaction forces. If a body is at rest, Newton's first two laws tells us that forces up equal forces down, and forces to the left equal forces to the right. If we have a body at rest, then no net force is acting on the body. If we then apply force to the body and it remains at rest, a reaction force opposes our applied force and is equal in magnitude and opposite in direction to the applied force. Consider the table to the right. There are no forces acting on it, so forces up equal forces down, since they're both zero, and the table doesn't move. If we place an object on the table, we would think its weight acting as the downward force would create a net force and the object would accelerate downwards, obeying Newton's first law of motion. Since the table does not move downwards, we know we have an upwards force equal in magnitude and opposite in the direction to our applied force. The upwards force that neutralizes the applied force, or the weight of the object, is a reaction force. The reaction force that opposes an applied force pushing two surfaces together is called the normal reaction force and is given the symbol Rn. In our example, the force pushing the two surfaces together is the weight of the object. If we increase the weight on our table, the normal reaction force Rn will at first increase to match our applied force. But at some point, if we keep increasing the applied force, the reaction force will reach a maximum value. If we then increase the applied force above the maximum reaction force value, the applied force, being greater than the reaction force, will accelerate the weight on the table in the direction of the applied force, which would be towards the floor. In this case, it means the stress on the table is too great and the table fails. When an applied force exceeds the reaction force, the object will accelerate in the direction of the applied force following Newton's second law. The accelerating force will be the difference between the applied force and the maximum reaction force. So, when a force is applied to an object, we can say the applied force equals the maximum reaction force plus the acceleration force. The important thing to remember about reaction forces is that they will match an applied force in magnitude to a certain value, then they can offer no more resistance. After this point, a net force caused by the difference between the applied force and the reaction force will cause the body to accelerate in the direction of the applied force. Example 2. The maximum reaction force a table can offer to weight is 200 newtons, What happens if a weight of 250 newtons is placed on the table? Step 1. Find the acceleration force. Applied force equals reaction force plus accelerating force. So our applied force was 250 newtons. Our maximum reaction force is 200 newtons. So plugging those numbers in our equation and rearranging our equation, we get acceleration force equals 250 newtons minus 200 newtons. The acceleration force equals 50 newtons. Step 2, finding the acceleration. Acceleration equals force divided by mass. Acceleration equals 50 newtons divided by 10 kilograms. Acceleration equals 5 meters per second squared in the direction of the net force. Rn is the normal reaction force that opposes an applied force pressing two surfaces together. In our previous example, the applied force was an object's weight. Now the weight of an object on the earth is constant, but the force it exerts pushing against the second object on which it rests can vary, causing Rn to have a different value. Consider the object on the table to the right having a weight of 500 newtons. As all of the weight acts to push the surfaces together, then forces up equal forces down, Rn equals W, and Rn is therefore 500 newtons. In the diagram to the right, we have the same object, but we are lifting vertically up on the object with a force of 100 newtons. Now we have the weight minus the lifting force, or 500 newtons minus 100 newtons, which equals 400 newtons, pushing the surfaces together. So Rn equals 400 newtons. Let's see how Newton's laws apply if we vertically lift up on the object. Because the object is still at rest, forces up equal forces down. Forces up equals Rn plus the lifting force. Forces down equals the weight of the object, W. So, forces up Rn plus lifting force equal forces down, which is W. Rn will therefore equal W minus the lifting force. Rn will equal 500 newtons minus 100 newtons. Rn equals 400 newtons. So if we lift vertically up on an object that is pushing two surfaces together, then the normal reaction force equals the object's weight minus the lifting force. If the lifting force equals the object's weight, then the force pushing the surfaces together is 0, and so is Rn. If the lifting force is greater than the object's weight, then the force up is greater than force down, and the object will accelerate upwards. In the diagram to the right, we push vertically down on the object with a force of 100 newtons. Now the force pushing the surfaces together is the object's weight plus the pushing force. Total force pushing the surfaces together equals 500 newtons plus 100 newtons equals 600 newtons. Since Rn equals the total pushing force, Rn equals 600 newtons. For Newton's laws, since the objects are at rest, forces up equal forces down. Rn equals weight plus pushing force. So Rn equals 500 newtons plus 100 newtons. Rn equals 600 newtons. So if we push vertically down on an object, the normal reaction force equals the object's weight plus the pushing force.